The possible energy outputs were calculated by Professor Munir and his team to see how much of a difference the enforced aspect and tilt angle had made. Clearly, much more energy could have been produced had the panels been sited at the optimum angle and aspect. The amount of electricity provided by a system like Napier's obviously fluctuates depending on the time of year and the time of day. Some form of power storage system is always needed to store the energy at times of excess production and to ensure a secure supply of electricity during periods of low output. In Napier's case, a connection to the national grid solved this problem. However, many communities in Scotland and around the world do not have access to grid electricity. Traditional battery storage is one option, however this is far from ideal because of the energy used and the toxic substances produced in battery manufacture. One solution currently under investigation at Napier University is the production of hydrogen, using the excess electricity and then in turn using this hydrogen as the fuel source when demand exceeds supply.
It's really important to emphasise at this point that before installing any renewable technology, the most important first step is to reduce consumption.
2,000 students use the Merchiston campus and hundreds of staff use the buildings for office space, alongside labs, computer rooms and cafes. Energy efficiency measures should always be employed first to reduce your demand to the lowest possible level. I cannot think of an exception where this is not the most cost-effective and environmentally sustainable approach. For the purpose of this video, we'll imagine that all energy efficiency improvements have taken place and that current demand is the level that we actually need to meet. The first step is to calculate that demand. I've used data from energy bills and from the Campus Energy Performance Certificate to plot current electricity demand. It's important to look at both the total consumption and the pattern of consumption to gain awareness of peak demand and dips in energy use. While we're looking at this as an overall picture, it's also important to look at the details of current costs of the system and current level of carbon emissions from this electricity in order to measure the impact that renewables would actually have and in order to calculate payback periods.
My next step was to select a widely available photovoltaic panel from a large manufacturer, again to give the idea of the weight, the size, the support structures required.
The selected panels cost £930 each and had an efficiency of 17.2%. And I've used this price as the basis for the calculation, but clearly this would be reduced dramatically if modules were purchased in bulk. Using this data alongside our calculated available solar radiation, it was possible to work out that each panel would produce 247 kilowatt hours per year. All photovoltaic panels lose a certain degree of efficiency at very hot temperatures. Generally, manufacturers measure efficiency at 25 degrees Celsius. Efficiency normally drops by about 0.5% per degree above this temperature. For once, the weather here is on our side. Professor Munir has kept temperature records in the past for this site and found that the temperature is only above 25 degrees for 11 hours in the year. On that basis, we can safely assume that the efficiency stays constant.
Now that we know how much energy each panel can realistically produce, we can start to think about how far we want to go and how much electricity we actually want to produce. We can start to factor in things like capital costs and loans and grants and start to work out our financial and energy payback periods.
Renewable technologies do not emit CO2 during use, but they use energy in their production and transport. This embodied energy can be calculated using a tool known as life cycle assessment. It's important to first set out the scope of an assessment. For example, are you calculating energy use from mining of raw materials all the way through to energy used in dealing with the disposal of the product at the end of its useful life? Are you thinking about pollution or waste? A full inventory must be compiled of all the materials that are used, and an impact assessment can be completed for each material. We'll focus on the embodied energy and embodied carbon in the solar panels under consideration, but really this is just one stage in a full life cycle assessment. It's important to note that different studies use different scopes of life cycle assessment. However, all studies show the same pattern while calculating emissions per kilowatt hour from electricity produced from different fuel sources. The panels that we've selected are monocrystalline, which has a higher embodied energy than polycrystalline due to the higher temperatures required in manufacture. Using the average results from available studies, we can estimate that each of our monocrystalline panels will have an embodied energy of 1.254 megawatt hours per 1.3 square metre panel. This then allows us to make the important calculation around the emissions per kilowatt hour produced by simply dividing the total embodied carbon dioxide by the expected lifetime output. It's interesting to note that our answer of 0.0681 kilograms of CO2 per kilowatt hour is startlingly accurate and is within 5% of the results of the detailed studies shown earlier. The results are also close to those found by Professor Munir when he completed a very detailed analysis of the embodied energy in Napier's current photovoltaic facade.
With this information, we've now got everything that we need to perform a full assessment of the financial and environmental impacts of investing in photovoltaics for the university campus. To help, I've developed an Excel workbook tool that really you could input anything about any renewable technology and it would come out with the output based on the available wind speeds, the available solar radiation at the particular site.
The output from these calculations shows that, for example, if we wish to meet 12% of the campus's electricity needs from solar photovoltaics, we would need to invest £1.7 million, which would have a financial payback period of just over 10 years, leaving the remaining years of the technology's life to make a profit. The energy payback period of the system would be just over 6 years. This option would actually use up 100% of the available roof space, would substantially reduce the emissions from the campus by 212 tonnes of carbon dioxide each year, and would consistently feed low carbon energy into the university's grid. If we start to look at using neighbouring roofs, or considering the use of walls, we could contemplate investing £6.5 million to meet 50% of the needs of the campus. Again, in real terms, the financial cost would be substantially lower if the technology was purchased in bulk. This level of investment would reduce emissions from the Merchiston campus by 44%, from 0.537 kilograms of CO2 per kilowatt hour to 0.378 kilograms of CO2 per kilowatt hour. It's when we think on this scale that we realise the true potential of these technologies.
All in all, the technology and financial incentives are enough to encourage organisations and individuals to invest in this technology. The incentives could actually do with being a bit higher to stimulate the mass investment that we need to reduce our emissions to acceptable levels. But even now, photovoltaics are a very shrewd investment indeed.